Hi, I'm Hannu Parviainen from Instituto de Astrofísica de Canarias, and I'm going to use my 10 minutes or so to give you a quick introduction to PyTransit. PyTransit is a Python package that implements a set of exoplanet transit models with a shared API. Its development started in 2009 and continues to date, with a new major version coming early this year. Here, I'll first give a quick overview of the API and then cover some more advanced features. First, let's start with basics. Modeling a transit in one passband without any complication features is easy. We begin by initializing the transit model, which in this example is the standard model with quadratic limb darkening. Then we give the model an array containing the mid-exposure times. Now we are ready to evaluate the model. Here K is the radius ratio, LDC are the limb darkening coefficients, and the rest are the orbital parameters. And as a result, we get a transit model evaluated at the mid-exposure times. If we want to model observations with longer integration times, like when modeling Kepler or TESS long cadence data, we can set the exposure time and number of subsamples after the model initialization. Then we evaluate the model exactly as before, and we get a transit model that is supersampled over the extended integrations. Next, we can complicate things a bit by modeling transits in different passbands. We can do this by associating each exposure with a light curve index. These light curve indices are just a way to group the data points into subgroups. That is, they're the code that some exposures belong to one group and some others to another group. Next, we associate each light curve index with a passband index. Passband indices connect each group to a passband. And in this example, we had 3 light curve groups and 2 passbands. Now we evaluate the model with 2 sets of limb darkening coefficients, 1 per passband, and get a transit model where the groups use different passband-specific limb darkening coefficients. After this, we can complicate things a bit further by assuming that the radius ratio can be different for each passband. This is useful, for example, when modeling low-resolution transmission spectroscopy. We can assign a different radius ratio to each passband simply by passing an array of radius ratios to the evaluate method, and we get, well, pretty much what we would expect at this point. Next, we can model datasets where some light curves need to be subsampled and others don't by giving the exposure times a number of subsamples as arrays, 1 value per light curve index. And yeah, you get the picture. Then we can also assign each light curve index an epoch index. After we've set the epoch indices, we can evaluate the model with separate transit center times for each epoch. PyTransit doesn't care where the center times come from. They can be free parameters in a fit, calculated using dynamical modeling, or so on. And here we have the previous models with TTVs. All in all, the last plot models 2 passbands with different limb darkening, radius ratio variations from passband to another, 2 very different observing cadences, and TTVs. And the transit model was created with this piece of code. We initialize the model, give it the mid-exposure times, light curve indices, passband indices, and epoch indices, and the supersampling info. And then we just evaluate it without parameters. Okay, let's move on to Roadrunner. Roadrunner is a fast transit model that can use any radially symmetric function to model stellar limb darkening while being faster to evaluate than the quadratic limb darkening model by Mandel and Argol. And next, I explain quickly how Roadrunner achieves this. A transit signal is basically just the flux from the star minus the flux occluded by the planet. If we had a star with a constant surface brightness, the transit signal would be the area of the stellar disk minus the area occluded by the planet, where we can compute the occluded area analytically using an equation for circle-circle intersection. Unfortunately, the stellar disk is not constant, but we have limb darkening. That is, the star's surface brightness decreases from the center to the limb. Now, the transit signal is flux integrated over the stellar disk, minus the flux integrated over the planet-star intersection area, normalized to the out-of-transit flux. The integral over the disk is straightforward, but the integral over the intersection area is trickier. Except that it's not, really. Because we can represent the integral as a product of the intersection area and the mean occluded surface brightness. The intersection area is again computed using circle-circle intersection routine, and the mean occluded surface brightness can be computed as a weighted average of the limb darkening model. Here, W is the weight function and I is the limb darkening function. Now we can turn the integral into a sum by discretizing the weight and limb darkening functions into one-dimensional arrays, which further simplifies to a dot product of the two discretized arrays. So, finally, we end up with a transit model where we first discretize the limb darkening model into a one-dimensional array and discretize the weight function into a two-dimensional interpolation table. After that, the transit model evaluation is nothing but a dot product of two relatively small arrays multiplied by the planet-star intersection area calculated using circle-circle intersection, which all is computationally very, very cheap. The model accuracy can be adjusted by changing the weight table resolution, and it is pretty fast all the way to sub-ppm level. And you get a complete freedom to model limb darkening any way you like. That is, the limb darkening model can be analytical, numerical from stellar models, or, well, nonsensical. For example, we can create a function that models the limb darkening as a damped harmonic oscillator. Then we just give the function to the Roadrunner model at initialization and evaluate the model. Or we can do the same with the step function. Good. Now we are moving to the last part of the talk, which is about a new Python package called MeepMeep. MeepMeep is a Python package that aims to model Keplerian orbits fast. It does this by cheating a bit and expanding the orbit into a bunch of Taylor series. The orbit evaluation has some overhead from the expansion, but after this everything is just sums and multiplications. Here I'm not going to talk about orbits in general, but about calculating the projected star-planet distance. Because the projected distance needs to be calculated for every single transit model evaluation, and it can take a large fraction of the whole transit model evaluation time. So, speeding up projected distance calculation can significantly speed up transit model evaluation. Luckily, MeepMeep has some special routines for the calculation of projected distances. First, we don't need the z coordinate, so we can expand the planet position in xy plane only. And then a single fourth order Taylor series expanded at mid-transit time is good enough for transit modeling. The approach is simple, uses college-level math, and gives highly accurate projected distances with a bunch of sums and multiplications, and one square root. And we don't need to solve eccentric anomalies or make calls to computationally expensive trigonometric functions, except when calculating the derivatives, what gives us a per-orbit overhead of about 1.5 microseconds. The evaluation speed using the standard Newton's method to calculate the eccentric anomaly is about 120 nanoseconds per call, while with this approach is about 1.3 nanoseconds. This is about 100 times faster, and even with the per-orbit overheads, this approach is faster if you are modeling a light curve with more than 13 points or a single Tesla Kepler long cadence point. The expansion to fourth order is also accurate even for quite extreme orbits with high eccentricity or small semi-major axis, and we can modify the approach a bit to suit single precision computations in a GPU easily. And the approach doesn't only give a speedy way to calculate projected distances, but also its partial derivatives with respect to the orbital parameters, because we can calculate them using a simple finite difference of the Taylor series expansion. So, we've already calculated the Taylor series expansion for the xy position. Next, we calculate the expansion for center time plus epsilon, period plus epsilon, and so on for all the 6 orbital parameters. And we get a new Taylor series representing the partial derivatives by simply calculating the finite differences between the series coefficients. And from these, we get the partial derivatives of the projected distance using the chain rule, where the partial derivatives of the x and y position are themselves 4th order polynomials, like this. So, the whole thing can be done with 7 lines of Python code, which calculate the projected distance and its partial derivatives with 14 4th order polynomials and 1 square root call. The overheads are about 7 times the overheads for projected distance, that is about 10 microseconds, and the evolution time is less than 7 times the projected distance evolution time, or about 10 nanoseconds. So we get the projected distance and all its partial derivatives 10 times faster than what it takes to calculate the projected distance using Newton's method. Now, when we have the partial derivatives for the projected distance, we can plug them into the transit model, in this case the Roadrunner model. Here we have the model, and here its partial derivatives with respect to the orbital parameters, where the circle-circle intersection and its derivative with respect to the projected distance have fast analytical solutions. The partial derivative of the projected distance with respect to the orbital parameter is calculated by meep, and the limb darkening and its derivative we calculate numerically. So, the current PyTransit version includes an API that makes modeling of heterogeneous light curves and TTV simple. The Roadrunner models allows you to use any radially symmetric limb darkening model, but is only slightly slower than the uniform disk model, and all the transit models use Taylor series expansion for the projected distance calculation. The next major version, 3, will allow to model variations in all orbital parameters and comes with further optimizations to the Roadrunner model and the ability to calculate the model's partial derivatives, with the goal being that the model and its partial derivatives is faster to compute than the analytical quadratic limb darkening model without derivatives. And that's it. Thanks.